I'm very excited to be here and to share my work about cosmic rays. So I'm going to start with a very brief roadmap.
Okay.
Yeah, okay. No, I did try it before, but here. So in this talk, we're going to go a little bit down a rabbit hole into cosmic ray physics. And this is a beautiful, uncanny valley, creepy picture of a rabbit hole in space made by Dolly. So I'm going to start by talking about cosmic rays and how they affect the circumgalactic medium, which is how I got into them in the first place. And then I'll start talking about how cosmic ray transport is severely underconstrained and how we can constrain it in the circumgalactic medium. And then we'll go a notch further into the rabbit hole and talk about models for cosmic ray scattering in the interstellar medium and how they are also underconstrained and how they can look differently from how we imagined, how they would affect these cosmic ray transport models that then will enable us to quantify it. And before I get any further, I want to pause to explain what I mean when I talk about cosmic rays, because they can be a lot of different things. So cosmic rays are relativistic charged particles, but as you can see on this plot, it can be a lot of different species and a lot of different energies. So when I talk about cosmic rays, I'm primarily talking about GeV-ish protons, which make up the bulk of the cosmic ray energy density in our galaxy. And a recurring theme that I'm going to be jumping back and forth between is that on AU or sub-AU scales, cosmic rays behave like particles. And so they are moving around magnetic field lines, and then perturbations in magnetic field lines perturb the pitch angle of that cosmic ray. But on galactic scales, we cannot hope to solve particles when we're trying to simulate a galaxy. Luckily, on these galactic scales, cosmic rays behave like a fluid, and we know how to simulate fluids. Great news for us. And this cosmic ray fluid affects galaxy evolution on all sorts of scales, from chemically enriching protoplanetary disks to ionizing giant molecular clouds, affecting star formation, to setting the structure of the interstellar medium, can drive galactic outflows that reach kiloparsecs or hundreds of kiloparsecs up to megaparsecs beyond the galactic disk. And in doing that, they structure the circumgalactic medium. And you might notice that this circumgalactic medium is the only panel that doesn't have a real picture. And that's because it is very difficult to detect in emission. So we don't actually have any pictures of the CGM. And it's really easy to think about galaxies as this part in the disk where all the stars are that emits light, and we can see it as a galaxy. But in reality, galaxies look something like this, where they're really surrounded by this large, very diffuse gaseous halo that, as it turns out, is really important for their evolution. But because this gaseous halo, the circumgalactic medium, is so diffuse, it really wasn't until the last decade that we were able to observe a lot of its structure in ultraviolet absorption. And so the basic idea is if you have a quasar, like a bright background source, whose spectrum you understand really well, and you have a galaxy halo in between you and this quasar, you can study the emission or the absorption lines in that halo that then give you clues about the composition of the circumgalactic medium. And so using this UV absorption spectroscopy technique, we now know that the circumgalactic medium isn't just some boring, quiet remnant of galaxy formation. We know that it has an incredibly rich structure that's shaped by chemically enriched outflows from the galactic disk. Those outflows, some of them leave the virial radius of the galaxy and never return. Some of them interact with the existing CGM. Some of them interact with inflows from either galaxy neighbors or from the pristine intergalactic medium. And so understanding the detailed structure of the CGM gives you clues as to the galaxy's history, and it gives us clues about what the future of that galaxy will be, and hopefully will help us understand why some galaxies keep forming stars while others die out. And there are a few interesting observations that have come out in these last 10 years about the circumgalactic medium that are puzzling theoretically, but as I'll explain later, I think cosmic rays can help with. So the first is that we now know that the majority of galactic baryons are in the CGM. So this is a plot showing the fraction of galactic baryons for Milky Way massive galaxies as a function of different components. And so for a long time, we've been able to roughly estimate the mass in the galactic disk. And if you look at the mass we expect from what we know about dark matter and the fraction of baryon, the mass in the disk is only about 20% of the mass we expect. And so in the last 10 years, we found that, yes, so the rest of the 80-ish% of galactic baryons are in the circumgalactic medium. And about 25 to 50% of all of those baryons are in this cool, warm phase. By that, I mean between 10 to the 4 to 10 to the 5 degrees Kelvin. And that's great news because this is expected to be accreted onto the galaxy and then promote future star formation. So yay, we have a reservoir of gas that can explain ongoing star formation. But it's a little weird because this gas is at the peak of the radiative cooling curve. And so we expect it to be short-lived. And so it's a little weird that there's so much of this gas in this temperature. Another really weird thing about this cool gas around low redshift L-star galaxies is that the cool phase appears to be out of thermal pressure. So if you start with the assumption of thermal pressure equilibrium, that seems like a reasonable place to start. You expect there to be a very straightforward relationship between the temperature and the density of the gas phases. And so if you know the temperature and the density of your hot phase, then you know the temperature for the cold phase or the cool phase, you can make predictions for the radial profiles of the gas densities of the two phases. But what we infer from observations of the low redshift circumgalactic medium is that the cool gas density is a lot closer to what we expect for the hot gas density. It's at least an order of magnitude lower than what we expect it to be if it were in thermal pressure equilibrium, which I think points to evidence for non-thermal pressure support. And then the last interesting thing about this cool and then generally multi-phase gas in circumgalactic medium is that it appears to be kinematically aligned. And so by that, what I mean is here's an example of an absorption spectrum from one of these low redshift L-star galaxies. The beige line is H1 in absorption, which traces roughly 10 to the 4 Kelvin gas. And this absorption feature is moving, say, 50 kilometers per second relative to the galaxy rest frame along the line of sight. But this spectrum also has a few different silicon lines and oxygen-6, which together trace about 2 orders of magnitude in temperature difference that are all also moving around 50 kilometers per second relative to the galaxy rest frame, which is weird because this sight line is really an integrated value, across the entire CGM at some impact parameter. And these are very different gas temperature phases. So it's not clear, why they should have similar velocities. But the fact that they do have similar velocities makes it really hints at there being some physical relationship between the gas phases. And this, kinematic alignment isn't a fluke. It happens again and again in these spectra. So one of the things we were trying to understand from the observation point of view is what is driving this kinematic alignment, and does it have any implications on the physical structure? Now the rest of my talk is going to look a little bit like this, where I'm going to talk about the ways in which cosmic rays can help alleviate some of these observational unknowns, and then we'll go from there. So before I jump into the simulations, I just wanted to give a brief kind of schematic overview of what to expect when you talk about cosmic rays in the galaxy and the CGM. And so the basic idea is that supernovae eject about 10% of their energy into accelerating cosmic rays. So you get a little dump of cosmic ray energy in your ion stem. Then those cosmic rays move away from their injection site with some effective transport rate. So this can be either diffusion or streaming. For now, we'll stay agnostic to that. It's just they move away from where they started. And as they move away, they set up a pressure gradient. And this non-thermal cosmic ray pressure gradient helps counteract gravity in maintaining hydrostatic equilibrium. So it can drive outflows, and it can, and once you have cosmic ray pressure out in the circumgalactic medium, they can couple to the thermal gas and have interesting effects on its state. So for example, the cosmic rays drive winds that are qualitatively different from thermally driven outflows. So this is an example from simulation of idealized ISM simulations, or the patch of the ISM. This top panel shows a thermally driven wind, and it's in time evolution to the right. And the color shows the gas column density. So you see for a thermally driven supernova outflow, you see like really kind of hot, bursty wind evolving to the right. But for a cosmic ray driven wind, it's much gentler. So these outflows are cooler, they're smoother, and they tend to have more mass loading, which continues at high galactic altitudes. And this gentle wind helps the survival of cool gas, which can explain why we have so much cool gas out in the EGM. Another way we can get cool gas in the circumgalactic medium is if it forms directly from the hot gas through thermal instabilities. And so one of the things that I've worked on in the recent past is studying these thermal instability simulations to see how cosmic rays affect the formation of cool gas and the properties of that cool gas once it forms. And so this is a simulation from that looks at an idealized patch of CGM gas. We seed an initial perturbation, and the colors show the slice of the density of the gas. And here we have gravity pointing down, so this would be like the galactic midplane somewhere down here. And there's rapid enough cooling so that you form cold gas. And the panel on the left doesn't have any cosmic rays, and the cold gas that forms behaves as we'd expect. It forms cold, dense logs that have densities that are as we'd expect based on the temperature of the gas, and they sink in the atmosphere. But as you add more and more cosmic ray pressure to the right, you see that as the cosmic ray pressure concentrates in the cold gas, you get really strange cold gas logs. So now all of a sudden you have very large, low density cool gas clouds that are more buoyant in the atmosphere. So they are sinking like all the way on the right, but they're sinking much more slowly, which might have effects on the kinematics and the accretion rates of cool gas in the galaxy. And so go ahead.
So Iryna, thanks. This is Brian from The Void. So in the maybe it's related. In the previous plot, you said that there's more mass and more cold gas going up. Is that because the cosmic rays are pushing the cold gas as well as the hot gas, whereas the supernovae only blast out the hot gas?
Yes. So the supernovae, especially in simulations, they often just inject a lot of energy, and sometimes they also inject kinetic energy explicitly. So you just get kind of like a fire hose effect where you're blasting out mostly hot gas, and like some cold gas gets entrained and may or may not survive the journey. Whereas in the cosmic ray driven wind, it's changing the entropy of the galaxy as like a function of latitude. So then you get a much more gentle kind of uplifting of the cool gas. Makes sense.
Yeah. Okay. Thanks.
One more question, if I may.
Yeah, please do.
The cosmic ray gas does not interact directly with either neutral or ionized gas. it needs the magnetic field to do that. What magnetic field values are you assuming when you have cosmic rays in the 4 panels to the right?
These specific simulations, I think, started with a plasma beta of 100. And so on the particle level, yes, they do really need the magnetic field to, couple, and I'll get to some of that a little bit later in the talk. For hydro simulations, you don't strictly need magnetic field lines because you could, approximate cosmic ray transport as isotropic diffusion. These specific simulations are part of a larger kind of parameter study so these, like this panel right here, actually doesn't have any cosmic ray transport. They're only infecting with a gas. And a little bit later, I'll show you what happens when you do include cosmic ray transport. Did that answer your question, or is there clarification that would be helpful?
I'll wait until you finish to see what you'll say about the magnetic field later and see if I have another question. Thank you.
Okay, thanks. So another thing that cosmic rays can do is they can really qualitatively change how the cool gas in your CGM looks like. So these are projections of the silicon-3 column density, which traces this cool 10 to the 4-ish Kelvin gas, and the CGM of 2 galaxies that are cherry-picked. One was run with AGN feedback, so it has very hot thermal pressure supported CGM, and the other one had added cosmic ray feedback, so it forms this really cool inner CGM. This is 100 by 100 kiloparsecs. And so in the thermally pressure supported CGM, you get normal cold gas or thermally normal cold gas, where it forms these cold dense clouds that are small kind of structures that are then sinking in your gravitational potential wells. Whereas in this cosmic ray pressure supported halo, you get a large, low density kind of volume filling cold gas inner region. And I know this is a really weird simulation, but this isn't the only one like it. I'll get to this point a little bit later, but basically every group that has run kind of galaxy simulations with cosmic ray feedback finds some version of an inner CGM that looks like this. And I think that's very interesting.
Iryna?
Yeah.
So there are galaxies that have had multiple supernovae in the last 100 years, actually, in the last 20 years. And presumably all of those cosmic rays firing off has had a direct impact on the CGM for these sorts of galaxies. Are there any observational studies of these nearby systems and ways to validate this against?
So it's really tricky to actually directly validate this observationally. Like, we don't actually know the difference between these two scenarios. So the gamma ray emission is a little too dim to really constrain, because you have such low densities. We did some work looking at synchrotron emission predictions, but that's also really hard. Like, once you get outside the disk, it's just really hard to measure with enough accuracy. But it's definitely a problem worth brainstorming. And so, as you might imagine, the kinematic properties of these two CGMs is very different. So this is a plot showing the radial velocity profile as a function of gas temperature for the 2 different galaxies I just showed you. And they're just color-coded to help visually with the cold and warm gas. And so in the thermal feedback galaxy, the cold gas has a different average radial velocity profile. And so this is actually an inflowing kind of merger, but you can see the bulk of the regular kind of cold gas just floating around the CGM has an average radial velocity that is offset from the hot phase. Whereas in the cosmic ray pressure supported galaxy, that cold gas radial velocity is actually pretty close to the hot gas radial velocity, which then translates to more kinematic alignment in spectra. But because we have simulations and not just observations, we can make mock synthetic spectra and see what they would look like, or see what they look like for the two different galaxy types, and then tie those to the physical state of the gas that's producing the spectra. So this is an example spectrum from the thermally supported galaxy. This has absorption from silicon-3 in green and oxygen-6 in red, and those trace kind of cool and warm gas components. And the x-axis is line of sight velocity. And so this specific spectrum was cherry-picked to show two cases of kinematic alignment. And then we can add the little particle data points that actually went into creating the spectra from the line of sight that went through the CGM. And we can link based on the velocities of the particles and the velocity offsets of the spectra, which to see if the kinematic alignment in the spectra has anything to do with the spatial alignment of the gas. And in this case, it does. So these dark red points, which have line of sight velocity of about 80 kilometers per second, look like they're coming from the same place in the light ray trajectory. So this is a case where the kinematic alignment in the spectra is actually coming from the same kind of physical structure for the cold and the warm gas. But this example is one where you have kinematic alignment in the spectra, but these particles that are causing the cool and warm gas are separated by something like 80 kiloparsecs. So they really don't have anything to do with each other. They just happen to have, a cold cloud here and a hot cloud there that were moving in the same line of sight velocity. Now, if I show you another cherry-picked example of the cosmic ray pressure dominating gas, we get a lot of slightly different behavior where we see a lot of kinematic alignment, and we see a lot more kinematic alignment that has some sort of spatial relationship. So here, even though this gas isn't directly spatially aligned, this is an interesting example of kind of a co-rotating envelope where you have a cold gas rotating with a galaxy and then a hotter envelope around that cold gas. And so that behavior is something that we didn't really see in the thermal feedback supported galaxy. But we repeated this kind of analysis for 100 sight lines per galaxy. And so for all the galaxies that had silicon and oxygen absorption, we quantified how the velocity offset in the spectra aligns with the spatial offset with the gas that is actually creating those absorption features. And so what we found is that in the cosmic ray pressure supported galaxy, and I should add that really this is only probing the inner CGM, so like that region where it really is supported by cosmic ray pressure. We find a relationship between the velocity offset and the kinematic offset of the gas. So if you see kinematic alignment in your spectra, it is likely to be from the same kind of physical structure or physically related structure. Whereas we don't see that same relationship in the thermal pressure supported galaxy. And so another way of thinking about it is that the more you expect kind of cold inflows to be an important feature in your CGM, the less likely it is that kinematic alignment in your spectra has something to do with the physical alignment.
I have to follow up. So
Yeah.
Does this mean that like in the same simulation, like thermal dominated cosmic ray, you are suppressing the influence at this stage, or is that just the example shows up more prominently of false alignment when you have got people in thermal?
I'm trying to think of how to repeat your question.
Yeah, you do that like the
Yeah.
slides where you had sort of that inflow show up.
This,
Yeah. So that inflow, is that then not happening in the cosmic ray feedback, or is that just sort of your like false positive case that you're trying to illustrate?
yeah, so the question is if the inflows in the cosmic ray feedback galaxy are suppressed. And in this case, I think these inflows really are suppressed, but you can, as I'll get to this a little bit, you can tweak your cosmic ray model so that you have more or less inflows, and that's not quite constrained. But I think So we're not at a place yet in our model where we can say like, it's not that this galaxy is the prediction for cosmic ray physics. It's more of an exploration of if you had a lot of non-thermal pressure support from cosmic rays, what happens to the state of your gas? And you, in this case, you get more buoyant, low density, cool gas that then naturally explains kinematic alignment and leads to more of a relationship between the kinematic and spatial. Okay, so I just showed a few examples of how cosmic rays can help alleviate some of these weird things we're seeing in the CGM, particularly the abundance of cool gas, the low densities of cool gas, and the kinematic alignment between gas phases. But there's a reason why I'm using very non-committal language here, as because cosmic ray transport really complicates everything. So there was a little bug in this earlier. Let's see if I can. One second. This movie refuses to play. Okay. Well, the problem is when you include cosmic ray transport, so if you let the cosmic rays move relative to the gas instead of just tying them into the gas, then that cosmic ray transport redistributes cosmic ray pressure from regions where it's concentrated, so in the cold gas, out to regions where it's not, in the hot gas. And the more effective that transport is, the more the cosmic rays decouple from the gas, and then they stop having this non-thermal pressure support that made the cool gas so weird. And so this plot is a family portrait of a lot of different simulations that I did in the parameter study from that movie I showed you with the density bubbles. And so what we did is we ran those same simulations with similar initial conditions for a variety of cosmic ray transport, a variety of initial cosmic ray values, initial magnetic field values, initial different cooling strengths. And so the y-axis is the cold gas that forms, it's the ratio of the cold gas density to the hot gas density. And as a function of the cosmic ray pressure, the ratio of the cosmic ray pressure to gas pressure in the cold gas. And then each of these points is time average value from the entire simulation. And they're colored by different cosmic ray transport physics. And so you can see kind of the short of it is you can get any answer you want as long as if you tweak your cosmic ray transport parameters enough. And that's an oversimplification of it, but it really highlights that if we want to make quantitative predictions for what is the cool gas density in the CGM at this time in this type of galaxy, we really need to understand how that cosmic ray transport is working and how to model it in galaxy simulations in order to be able to do that. And in particular, I am interested in applying this to the CGM because in my work and in the work of several other groups, we consistently see the formation of the cosmic ray pressure supported inner CGM, for a variety of cosmic ray transport models. And I think it's really interesting to think about the galaxy as having this really highly kind of non-thermal inner halo region, but we can't really tell the difference between a cosmic ray pressure supported inner CGM or a CGM where cosmic ray pressure isn't really important. And we can't really tell that observationally yet, and we don't have the theory to definitely, say one way or the other. Which brings me to, the next step in the rabbit hole of constraining cosmic ray transport models. And so if I could summarize the problem, I like using this toy plot, which shows the effective cosmic ray transport rate as a function of distance from the galaxy center. And again, when I say cosmic ray transport rate, I'm using kind of an agnostic term to mean either the diffusion coefficient or the streaming velocity. I just, trying to be agnostic about the exact way that they're moving, but just saying they are moving in the galaxy at some rate that maybe responds to the properties of the galaxy. And all of our observational constraints really constrain the cosmic ray transport rate in our local ISM region. And we don't know if or how we can take those transport rates and apply them to other galaxies or other regions of our own galaxy. And there really are models that can reproduce the existing ISM transport rates, but then diverge from each other by up to 10 orders of magnitude in their predicted cosmic ray transport rate in the circumgalactic medium. And so there are a couple of ways of going about solving this problem. One is to try to directly constrain the cosmic ray transport in the CGM. And so one of the ways we've done this is by we made a toy model that can take 3 observables of the CGM and use them to make a prediction for the lower limit of the effective cosmic ray transport rate. The idea is, if you're observing the CGM with absorption studies, you have some integrated line of sight that goes through CGM, and some impact parameter. And so the key components you need are the average star formation rate, ideally averaged over a couple of giga-years, which will probe how much cosmic rays you're injecting into the ISM. And assuming that all of those cosmic rays aren't getting destroyed in the ISM, which is a reasonable assumption for regular non-star bursting galaxies, then those cosmic rays will make it out into the CGM, and they'll affect the total hydrogen column density. And then you have one more term for the circular velocity that kind of is a proxy for the mass of the galaxy and its gravitational potential well. And so using this model, I worked with a high school student at the time, Shreya Nakum, who is now a freshman at UC Irvine as of a few weeks ago. And she went through the COS Halos published galaxies, and she looked at their the modeled total hydrogen column densities, the average star formation rates, and she made models for their circular velocities based on their coded star formation mass or stellar masses. And she came up with these estimates of the lower limit of the cosmic ray transport rate out in the CGM. And so this is really exciting because this is our first kind of data set that has some quantitative constraints on the transport rate in the CGM. And so one thing we can get from this is, so this plot is just a slightly more technical version of this plot on the right. We know that in our ISM, the shaded or cosmic ray transport rate is roughly this shaded region, from 10 to the 28, 29, depending on some details we can pull away for now. We know the transport in the ISM is something like this. And so if we expect the cosmic ray transport rate in these other local galaxies or nearby galaxies is similar, then these data points out here, which are, I don't know, this line is about 40 kiloparsecs, depending on the virial radius of these galaxies. This is a pretty clear indication that the cosmic ray transport rate has to increase out in the outer CGM, which effectively rules out this bottom region of transport models, which is really exciting. But there's a lot more work to do. And the challenging thing is estimating the total hydrogen column density, just because we're usually sensitive to either one phase or the other. It's hard to model for all of them, but there should be a lot more data coming soon with FRBs. So either stay tuned, or if you're working on observing those, come talk to me. Another thing we've been working on is with Sam Panada, who is a 5th-year graduate student in Caltech. He wrote a really detailed forward modeling of synchrotron emission from the fire galaxies, which takes into account magnetic fields and the spectrally evolved cosmic rays to make predictions for the synchrotron intensity. And so this is an example of 2 galaxies run with a fire simulation that both of these reproduce all of the required ISM observations, but they clearly look very different, both qualitatively and quantitatively in their prediction for synchrotron emission. And so you can use this to either make radial profiles or find other ways of predicting kind of differences in the synchrotron emission from different galaxies. But we still have a bit more work to do here on both kind of doing this for more cosmic ray models, as well as trying to think of ways we can really highlight these differences so that we can observe them with existing instruments. Yeah.
Just a very basic question. Do the protons and electrons do the same thing, or do they not? Or do you not know?
Not quite. So it turns out, so Sam has another paper that I don't have up here that just came out like last month or so that shows that it actually is important to explicitly evolve your cosmic ray electrons, because if you only evolve the protons and then make assumptions about what the electron spectrum should be, you're going to get some of these features wrong, or at least different from like if you explicitly evolve them. So yeah, this is getting computationally expensive fast. Right, so another way of constraining cosmic ray transport is to focus back here where we have our observations and try to think or try to come up with a robust theoretical model for the underlying scattering physics that is then leading to this bulk transport rate, which brings me to my last step in our rabbit hole. And just to start fresh, because I've been using a lot of different terminology, I just want to highlight that when I'm talking about small scales, sub-AU, cosmic rays behave as particles, so they move, or as charged particles, so they move around magnetic field lines. And if you have fluctuations in the magnetic field that are of order of the cosmic ray gyro radius, then that's going to perturb the pitch angle of the cosmic ray. So that, and if you get enough of these pitch angle perturbations on large scales, you're going to get a diffusive like behavior that we call transport, and then we model as a. And so the good news is, observationally, we have the average scattering rate constrained pretty darn well. And we know that this average scattering rate has a power law dependence on the energy of the cosmic ray. And so this part is kind of, I'm going to take as our kind of cornerstone assumption that we have this right. So this is, observationally agreed on within pretty reasonable limits. And if you take the scattering rate and you plug it into your fluid equations and then run a galaxy simulation with it, you actually reproduce all the observables again, which is a good sign. It means working as intended. We know the average. The problem is we don't know what causes those magnetic fluctuations that then leads to this average cosmic ray scattering rate. And if we don't really understand what causes these magnetic fluctuations, then we don't know how to extrapolate this average scattering rate into other regions of the galaxy. And so the problem here is that, I guess let me back up. So the general basic idea is that cosmic rays are generated in galactic supernovae. They travel around magnetic field lines before hitting us or before being observed at the Earth. And traditional theories of cosmic ray scattering tend to assume that cosmic rays are scattered continuously throughout the volume filling ISM. And in order to do that, they assume that small scale perturbations, well, all of these are small scale perturbations, but smaller fluctuations scatter low energy cosmic rays, and slightly higher energy cosmic rays are scattered by larger fluctuations on the order of their gyro radius. And so the problem here is that in order to produce this average scattering rate, having this model imposes a specific power spectrum of the magnetic field fluctuations that have, as of recently, turned out pretty difficult to explain theoretically. So kind of the base, like the two cornerstone models are either that cosmic rays are scattered by fluctuations that are caused by a turbulent cascade that goes all the way down to these AU scale, or that cosmic rays themselves generate these fluctuations. But both of these models have some fundamental flaws that prevents them from obviously kind of producing this correct scaling relation. And so instead, what we've been thinking about lately is, well, maybe cosmic ray scattering doesn't have to happen homogeneously throughout the entire ISM. Maybe it happens in kind of discrete patches, and in between those patches, the cosmic rays can free stream at the speed of light or near the speed of light. And so in this model, the cosmic ray, when it encounters a patch, would be strongly scattered in a very brief amount of time, and then it would escape and travel a mean free path before hitting another such scattering path. And in this side, the key thing here is that small scattering patches would only scatter lower energy cosmic rays, meanwhile, larger patches would scatter both low energy and higher energy cosmic rays. And so in this way, in order to reproduce the dependence of the scattering rate on the cosmic ray energy, you can achieve this by imposing some sort of size distribution of the patches as opposed to the power spectrum of the magnetic field. And so we played around with thinking about different properties that these patches would need to have. And so one kind of obvious thing to look into is how the size of the patches would scale as the number density of the patches in the ISM. And so for fixed mean free paths, which are a function of the cosmic ray energy, we would need these kind of shaded contours to explain scattering for MeV, GeV, and TeV cosmic rays. And so an ideal kind of macroscopic structure should intersect all of these models, like, roughly like this. But the problem is, when we thought about the macroscopic structures in the ISM, none of these were even close to intersecting. Either they were all too small for their number densities, or not nearly abundant enough for their size to explain the cosmic ray scattering that we see. And to clarify, doesn't mean that these structures don't scatter cosmic rays. I mean, we know that the heliosphere scatters cosmic rays, but it's just that they on their own don't produce enough cosmic ray scattering to observe, to explain the observed amount of cosmic ray scattering. So another thing we looked into is the volume filling factor as a function of the size of the potential scattering patches. And in this case, if you had something that looks like this, you could explain the observed scattering, or the cosmic ray scattering. And there aren't any actual things or actual candidate theories on this plot, because we don't really have constraints on some of these things that could be causing this scattering. For example, it could be due to intermittence and turbulence, tiny scale atomic structures, or extreme scattering events, which are radio phenomena that we don't quite have a working model for yet. Could be weak shocks in the ISM, could be magnetic features like plasmoids or magnetic islands. And so these are all plausible kind of features of magnetic fields that could be or could be structuring the small scale ISM that we're then going to explore and follow up idealized studies or idealized simulations to see, one, do they effectively scatter cosmic rays, and then if they do, what are the observational signatures that we would expect maybe in the ISM, to see if we can try to constrain whether or not cosmic ray scattering is patchy or continuous. And so to climb out of this cosmic ray rabbit hole, cosmic ray scattering might be intermittent, or maybe it's not. But I think we're finally getting to the point where we're close to figuring out what is scattering cosmic rays, which is then going to unlock how we should be modeling cosmic ray transport on galactic scales, which is then going to give us predictive power for how this cosmic ray fluid affects galaxy evolution on a variety of scales in our galaxy and in other galaxies. So thank you for your time. I would love to take your questions.
Sorry.
Go straight forward, Telemarcus.
I didn't hear you, sorry.
Please go ahead and ask your question.
Thank you. I have two quick questions and a comment. What equation did you use when you included cosmic rays for the time rate of change of the cosmic ray pressure? That's the first question.
Sorry, time rate of change of the cosmic ray pressure in which?
You have to evolve it, right, in the simulation. What is the actual equation used for that time rate of change?
We evolve it. So, and it's a little different in the different simulations I showed. So, the first few simulations they've evolved as a second fluid, so the energy is explicitly evolved much like the gas energy, only has a different adiabatic index. And so it has, in those simulations, it's either diffusing or streaming. In some of the later, like the synchrotron simulations from the fire galaxies, they use a reduced speed of light, kind of 2-moment method. I don't know if that answers.
Well, sort of. In other words, there is no actual equation for that time rate of change you are using. You are parameterizing the pressure as a function of the density of the cosmic rays, right?
You mean the cosmic ray pressure from the cosmic ray density, or I'm just not understanding.
Normally in a simulation, you have to have the time evolution of the cosmic ray pressure present.
Yeah.
And I was asking, what is the right side of that equation? Because it has been problematic over the decades, and I'm wondering what you are doing with that.
So the time evolution contains the advection with the gas, the streaming, the diffusion. And so that's for the first few simulations. And then the other simulations there's a newer approach to simulating cosmic rays akin to like radiation. And so that uses a 2-moment method that explicitly involves both the cosmic ray pressure and the flux. So they can kind of self-consistently go between kind of more free streaming and more self-confined modes. Okay.
The second question is, back in 1969, Kalsrad and Pierce showed that the cosmic rays, spin a relativistic gas, tried to propagate with essentially the speed of light divided by the square root of 3. However, in a very nice proof, they showed that when cosmic rays try to do that, they are limited by the Alfvén speed of the thermal gas, which is a few tenths typically of kilometers per second. Have you included that effect in your simulations?
Yes, so these simulations, all of them include some form of Alfvén streaming or some form of cosmic ray streaming at the Alfvén speed. There's kind of towards the later half of my talk, there's kind of, well, all papers have pointed this out, but there's also been some new kind of simulation evidence that in this streaming approximation, you tend to get a runaway effect where either the cosmic rays become over-confined and they stop streaming at the Alfvén speed, or they are under-confined and they escape. And so there's some issues. It's unclear if this effect can be responsible for the overall transport in the galaxy.
Sure, thank you. A quick comment. Back in 1975, in a paper in Astronomy and Astrophysics, I showed that the dot product of the magnetic field vector and the gradient of the cosmic ray pressure is 0 along field lines, which means that if you have a flux tube, part of which is characterized by a strong magnetic field and therefore high gas pressure, and another part by weak magnetic field, low gas pressure, the cosmic ray pressure and density is equal along that flux tube, is related to a point that you made earlier in your talk.
I'll have to look into that. I wasn't familiar with it.
Brian, I noticed your hand was up earlier. Do you have another question?
Yeah, so Iryna, thanks for your nice talk. So in the last discussion you had, where you had the scattering happening at different with different mean free paths for different particles. So how does the magnetic field fit into that? So what's the relationship between the mean free path and the magnetic field? I mean, the particles are still spiraling around the field lines, right?
Yeah, so the magnetic field gets tied into the rigidity of the cosmic ray. Really, this should be the rigidity, and I just simplified it to reduce jargon, but
Sure.
So I think the mean free path, it's not meant to be like an exact quantity. It's kind of order of magnitude at this point. And yeah, I think the magnetic field just gets looped into the rigidity. So it will affect it, but probably not by more than, let's say, an order of magnitude on either end of like the range that we're looking at. And right now, the kind of, we have a lot more uncertainties than that for this regime.
Yeah. Okay. Got it. Thanks.
Actually, related to this as well, can you go back to that MEV macroscopic slide and the comparison that you had to different lengths?
Different.
Yeah, size of batteries. So you have one more piece of information. You actually know number densities of things like supernova remnants and giant molecular clouds. And given that you have those, and you sort of know the galaxies that are producing these cosmic rays in some detail that you're studying, could you actually look and see which ones are consistent? Like, are there enough patches to actually reproduce the existing cosmic ray scattering?
Yeah. So I think
I'd be shocked if there were enough supernova remnants in a galaxy to say just SNR patches there.
Yeah. Actually, so they're kind of hidden, but we have supernova remnants down at this bottom end. So I think it's highly unlikely that supernova remnants or other kind of macro scale structures in the galaxy are causing the total.
So they have no role to play at all?
Not necessarily. So they could be scattering, or they likely are scattering cosmic rays. Well, I guess there's kind of two separate questions. So one is, what is causing kind of the bulk of the scattering we observe? It's likely not this. The other is like, how are cosmic rays just scattered in general in some of these structures? So we could do something like look at the synchrotron emission from, say, the supernova remnant, but that gets kind of tricky because there's also, we need to kind of model out there's the cosmic ray separation mechanism, and then there's how much, like, we need to really know what we expect the cosmic ray energy density to be before saying like, oh, here's how we, so clearly the magnetic field structures in this structure are, affecting cosmic ray transfer in this way.
Other questions?
I don't know much about cosmic rays, so I have really some basic question. Is there, if a galaxy has a really high star formation and there's going to be more cosmic rays, but is there a threshold above which there's just so many cosmic rays being produced that all these models are like absolutely?
So the question is, if a galaxy has a really high star formation rate, if that could they produce so much cosmic rays that some of these models kind of go out the window? And it's a really interesting question because we don't know very well. I think an interesting thing is the starburst galaxies. So the kind of some of the models I showed earlier assume that cosmic rays, once injected in the ISM, can escape without losing too much energy by to gas interactions. And galaxies like starburst galaxies, cosmic rays can actually lose a very significant amount of their energy in the ISM. So that could look very different in terms of both what they do to the ISM structure and then how much cosmic ray energy is left over into making its way out into the CGM. And then there's also AGN feedback, which we think like probably producing cosmic rays, but we don't have that constrained by like at least an order of magnitude. How much cosmic ray energy are they injecting?
Maybe this is like a big question, but how do you simulate cosmic rays? Do you treat them as particle or do you look like?
Yeah, so the question is, how do we simulate cosmic rays, whether it's as a particle or something else? So in galaxy scale simulations, what is usually done there is its own fluid that then couples to the gas. So you have, your regular gas equations, and when you're calculating the total pressure, you include the cosmic ray pressure, and then separately the cosmic ray fluid evolves via its own equations that then can advect with the velocity of the gas, and then relative to the gas via some transport prescription that is the unconstrained part. And they can also have some energy loss terms in between the gas.
So maybe I missed this, but this is like so in your work, this is like isolated galaxy, right? Or do you like simulate the whole universe and cancel?
So most of my work has been isolated galaxy simulations with some kind of idealized patch of CGM like gas.
So do you think like concentration on the galaxy can significantly impact the CGM?
So the question is if this cosmic rays from other galaxies can affect the CGM of our galaxy. And I think it's unlikely because if cosmic rays are so in order to have an effect on the gas, cosmic rays need to be moving relatively slowly, or let's say diffusion coefficients of 10 to the 28, 29 centimeters squared per second. And if that's the case, then they wouldn't really have had enough time to kind of travel from another galaxy into our own halo. You could have something like a merger that then exchanges cosmic ray pressure, but it's not like you have two separate galaxies where one produces cosmic ray. Make it to you.
Great. Well, basically at time
Definitely great. Roughly for this model, I'm curious, how does the distribution of cosmic ray sources affected at all? Does it matter if it's supernova or if it's from the AGN? If that's significant, that results in a different preference?
The question is it for this model specifically? The question is if the source of the cosmic rays affects like whether it's supernova or AGN affects this model. And it's not really, I guess the relevant effect of the AGN would be like if it injects a different spectrum of cosmic rays than the supernova
spectrum, or also even different distribution within the galaxy.
But different distributions within the galaxy. All you need is, well, the premise of this model is that even one scattering patch would be enough to completely isotropize the cosmic ray pitch angle distribution. So unless you're like right next to a source that hasn't had time to hit any of these, patches with a mean free path like 10 parsecs, you're probably not in a regime where you know the difference.
Okay, well, we are at time. Let's thank our speaker again so we can look at a little bit of questions. I'm sure